Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. This is the 6th video in the series on vector network analyzers, or VNAs. In the previous video, we did the foundations of doing two-port calibration and measurement. It was going to be a single video, but it got way too long, and I just didn't feel that it was a good thing to put it all in one place. So I broke it up into 2 videos. So if you've stumbled upon this first, it would be a really good idea to go back to the previous video and watch those foundations first before we get into the actual demonstrations here. We're going to be demonstrating how to make measurements on 2 different kinds of devices. We have this passive device. It is a bandpass cavity for the VHF range. We're going to be making measurements on its insertion loss using a 2-port VNA. We're also going to be measuring the gain of this Receive Pre-Amp and this little amplifier using our VNAs. If you find this video helpful, please click on like and subscribe to the channel so that you will get notifications of future videos. With that, let's get into our demonstrations. Our first demonstration is going to be to look at the frequency response of this Wacom bandpass cavity. Now we know that this is intended for the amateur radio VHF 2-meter band, which runs from 144 to 148 megahertz. We notice that we have the SO239 or UHF connectors for both the input and the output. Also, we see here on our miniVNA Tiny, we have SMA connectors. So somehow I have to get to this SMA connector to these UHF connectors. I choose to use these SMA to BNC cables that I have, along with a BNC to UHF connector. And then in order to do the calibration, I'm going to need a through. So I have this female to female through connector to use. As far as signal levels are concerned, because this is actually intended to be used as a transmit filter, I'm sure that the -6 dBm that this miniVNA Tiny puts out is not going to hardly tickle its side. So let's go on and do the calibration. Alright, so we're all ready to start the actual calibration. I have my cables connected to my SMA connectors all the way down to the adapters connected to the end. I have the cables appropriately spaced from one another, and I have my female-female connector I'm going to be using as my through adapter for the calibration. Now let's go through the actual calibration using the software. So I just opened the application for the miniVNA Tiny, and you'll notice that it kindly reminds me that there's no calibration data available for the mode, but it doesn't have a mode here. So I am interested in doing transmission, and it says I'm not calibrated again. Now I can either click here to go to create the new calibration set, or I can do calibrate, create. The first thing it wants is an open. Now, as you recall, the 2 cables that I have connected up to my miniVNA Tiny were nicely spaced from one another, and I am going to choose mode 1, which takes a little bit longer to do. I have set this up so that the range of frequencies I'm interested in has a lot of calibration steps and overscans to give me the best accuracy I can possibly get. So here we go. We're going to read the open. All right, we have completed reading the open. And now I'm going to connect up my adapter to do the loop. And now that we're connected, we will do the loop. All right, we now have the loop completed. Now I can save this calibration data into a file if I intend to use these cables and these adapters and everything again for another measurement. I could save it into a file here so I can quickly recall that calibration data and not have to go through this again. But even if I do this, I still have to click on the update, which updates the current software state with the new calibration data. We still don't have anything on the screen. The only thing we're really interested in is the transmission loss at this point, which is the same thing as the through transmission. And I'm not really interested in the phase, but so I'm going to click on none there. And I'm going to do a single scan. But first, I have to set my frequency limits. Remember, we didn't set them for calibration because we're not allowed to until such time as we have a calibration. So 144 M for meg. 148 M for meg. There we go. And then we do a single scan. So I'm scanning the entire 2 meter amateur radio band because it's, oh, look at that. Isn't that real nice? Right around 0.01 dB. You know why? Because I haven't connected up the unit under test. All right, so we're going to do a single scan. That just shows that the calibration was doing what it was supposed to do, coming up with 0.01 dB of insertion loss. Well, we discover where we're tuned. We're tuned right here. But let's say we want to zoom in on this to get a better view of it. I mean, we're looking at a lot of frequencies here. So let's say we want to go from 147-ish. So I click on that spot to set a marker. I hold down the shift and I go up to the top end here, and that sets marker 2. And then I can click on zoom, and it resets the start and stop frequencies to those limits and does a scan right away. So here we are. This is what our filter looks like, and it looks like the peak is right here at 147.676792 megahertz. And it has an insertion loss at that point of 1.15 dB. Now you could go down here until you find the 3 dB point away from that in both sides and discover what its bandwidth is, because that's the definition of a bandwidth, is 3 dB points. So you go down 3 dB from there, 3 dB over here, and discover what the bandwidth of this is. Now, let's go through this same process with the higher end VNA. All right, we're going to be doing the same cavity, and it still has the UHF connectors on it. And then we come over to the VNA and we notice that it has N connectors on it. So I'm going to use my handy dandy cables here that have N connectors on both ends to connect up to the unit under test. And then I'm going to use these N to UHF connectors to connect up to the unit under test. And then this UHF female to UHF female to operate as my through. Alright, so now we're ready to go here. We got our cables connected up there. One is threading along the bench top. Got my adapter in place. Got my other guy with the adapter in place, threading along here. We are ready to do our calibration and measurement using the Tektronix VNA. Step 1 with the Tektronix VNA is to set our start and stop frequencies before we do any calibration at all. So we're going to set our start frequency for 144 M for meg and our stop frequency for 148 meg. And so now you can see 144 to 148 megahertz. And now we want to do our calibration. Now we have several options here when we go to calibrate. There's response, there's enhanced response, there's 2-port SOLT. So for the sake of simplicity, we're just going to hit the response, and we're going to go through response through. And we want S21 because our source port is port 1. Our measurement port is port 2. And so you can see all it wants is through and isolation. So in order to do through, we have to install our adapter between the two. And then we click on through. Next, it wants isolation, which means I just disconnect the two cables from one another and keep them separated. And here we go with isolation. And now we click on apply. And we are ready to go. Now, format, we want log magnitude. Measure, we want S21. And notice the two cables are disconnected from one another, and you can see we have 110 dB of isolation between them. So let's see how they operate in with the cavity here. There we go. Okay. It's just this little bump here. So let's go to scale, and we're going to auto scale so that we can see things better. And even there, we could probably make that better, but we want to zoom in here. We can see our little peak is right here. We want to zoom in to this point here. So we're going to change our start frequency. Remember, it's okay to calibrate wider and go narrower. You lose some accuracy by doing that, but for the sake of what we're doing, the loss of accuracy is going to be minimal. So I'm just going to change the start frequency to 147 megahertz. And it looks like a little bump again. Let's re-auto scale. There we go. Now I could set up a marker 1, and drag this around and use my calibrated eyeball to find the peak point here. But I also have this search function, and I could say I want to search for the peak. So let's just move this down here so we can see it actually do it. Search peak, and there we are, 147.655 megahertz. According to this VNA, it has an insertion loss of 1.07 dB at this frequency right here. So there you go. We have done a 2-port calibration and measurement. Now just by way of reference so that you get a chance to see it, if I go to calibrate and we look at enhanced response, we choose S21. Notice it comes up with open, short, load. This is calibrating port 1 for a single port type measurement, and then the through and the isolation is doing a 2-port between ports 1 and 2. If we were to do this one, which is between port 2 and 1, you would see that, again, this time it's calibrating port 2 of the VNA as a single port measurement. And then between ports 1 as the source and 2 as the detector for through and isolation. If, on the other hand, we go to 2-port SOL, now SOLT, this is short open load through. Notice that now we're doing a full 2-port calibration. It does a 1-port calibration, open short load on port 1, a 1-port calibration on port 2, open short load, and then a complete calibration between ports 1 and 2. So there you go, higher end VNA, 2 ports on a passive device. Now, let's talk about doing an active device. When we're talking about making a measurement on a 2-port active device, we have to be more concerned about levels. We have to think about the unit under test. We have to consider what its maximum output level. And we have to think about how much gain is this device going to have. We need to consider the VNA's input level. Well, in the case of our particular active amplifier, it is a receive RF preamp in the 2-meter band. And so we're going to assume that it wants to adhere to receive level type signals. Now in the radio world, there's the S meter on the radio, and by convention S9, which is mid-level on that meter, S9 is the same as minus 73 dB or 50 microvolts. Now a lot of the S meters will be S9 plus 10 plus 20. A lot of them max out around plus 60 dB. So if we do the math, minus 73 dB signal level is S9, and S9 plus 60 dB then becomes minus 13 dB. So we kind of make an assumption at this point that our unit under test is not going to want a signal greater than minus 13 dB on its input. But not only do we have to think about the input side of this amplifier, we have to consider what is its output. I mean, we could put in minus 13 dB, have a gain of 20 dB like this particular amplifier is supposed to be, and the result over here would be a plus, well, let's see, 20 plus 7 dB. Well, what if the output of this can't do plus 7 dB? Well, then, then you're going to get an indication of gain that is lower than it really is at real levels. So what you have to say then is, okay, this is going to be feeding in the real world. The output of this ends up going to another receiver. And we're going to make the assumption that this is designed to accommodate the limitations of this receiver. That being the case, then, we can say that this receiver probably has this same limitation to it. So minus 13 dB is the maximum that we want our RF preamplifier to have. So the VNA with this 20 dB of gain in here is going to see no more than minus 13 dB of a signal in order to accommodate the fact that this is probably designed to talk to a receiver that has this kind of limitation, so let's not exceed that limitation. Well, what does that mean then? If we have 20 dB of gain potentially here, and we don't want the output to be more than minus 13 dB, that means that over here our input shouldn't be any greater than minus 33 dB. So now we've planned for the maximum possible output of the unit under test. We've planned for the maximum possible input to the unit under test. But we're still faced with a problem. Our VNA has, let's say, 0 dB of output power. Or in the case of the miniVNA Tiny, minus 6 dB. But that's still a far cry away from this minus 33 dB. So how do we accommodate that? Well, the higher end VNAs, like I said earlier in this video, the higher end VNAs will let you make some adjustments to its output power. And that might be sufficient to be able to get down here, but it might not too. So be prepared, like with the miniVNA Tiny, we're going to have to insert an attenuator here so that we can take this minus 6 dB that the miniVNA Tiny is putting out and turn it into minus 33 dB. Well, you know, we really don't want to push the edges of the limitations. This is like a maximum input is minus 33 dB. We don't really want to do minus 33 dB. So why don't we, in this case, decide to use a 35 dB attenuator here. So what does that give us? Well, for the miniVNA Tiny with the minus 6 dB, that means that our actual input here is going to be minus 41 dB. And that's okay. With the additional 20 dB gain, we get something over here, because who knows, maybe this unit that we're testing has higher gain than 20 dB. Or maybe the miniVNA Tiny says it's minus 6 dB out, but maybe it's not really minus 6. Maybe it's minus 5 or minus 3. You know, we don't know exactly. This is just the specification. So in order to stay within everything, we would rather be a little conservative using a 35 dB attenuator here. Now with my HP VNA, the lowest I can adjust my power level is minus 10 dB, so I could use a 25 dB attenuator here, or a 30, let's say a 30 dB attenuator here with that one. With the Tektronix VNA, the newer one, I can actually adjust the output of my VNA all the way down with a source level of minus 35 dB. So I don't even need to use an attenuator for that one. So what we're going to end up doing is we're going to set up our miniVNA Tiny. We're going to use a step attenuator box to give us about 35 dB of attenuation. And then we're going to calibrate everything and make the measurement. So let's step through that process. Now, because the miniVNA Tiny does not allow me to calibrate it with this much attenuation in line, I'm actually going to have to measure the characteristics of my attenuator across that set of frequencies first, which means I have to calibrate my miniVNA Tiny with just the BNC connectors, and I'll use this as my through adapter for the calibration. I will then characterize my step attenuator through those frequencies, save the data in a spreadsheet file, and then I will recalibrate using all of these other adapters in order to accommodate this will take the place of the attenuator in the second calibration, by the way. And then once we're done with all of that, we will actually measure the gain of the amplifier. Well, here we are at the residual from our Wacom experiment or demonstration. And now we're getting ready to recalibrate because we're going to be doing that active calibration. The first step is to characterize my attenuator box across the set of frequencies that we're interested in. So we're going to recalibrate just for that particular thing. Now my cables are laying out and they're all separated, so I can just click on Read Open. It has completed the reading of the open cables. Now I'm going to connect the two cables together using my BNC to BNC adapter. And so now we will read the loop. It has completed reading the loop. And as I stated before, I could save this calibration data here for later use, so I don't have to sit around and watch it do its thing. But we're going to update, which sends this calibration data to our software. And now we set our start and stop frequencies, which is 144 M for megahertz to 148 M for megahertz. Now we connect our cables up to the attenuator so that we can see what its performance is across the entire 2-meter band. We're now connected. We're not interested in the phase shifts, so we're just going to shut that off. All we're interested in is transmission loss, because all we're doing is measuring the gain of this amplifier. So we'll do a single scan. And there we go, right across the entire 2-meter band. Now, what we want to do is we want to export this data to an Excel file. Notice that we can also do a CSV file. Oops, a CSV file if you're not using Excel. But I use Excel, so I'm going to use the Excel file. It has put it in its special little place here. And OK. Now we're going to get ready to do the calibration necessary to do the actual measurement of the gain of the amplifier. So now that we've fully characterized our high-end, clearly superior, I say that tongue-in-cheek, step attenuator for our test. Now we have to recalibrate the miniVNA Tiny to get ready to do the gain measurement of this guy. So I'm using the same cable here to the BNC. Now this end of the BNC will end up connecting to one end of the attenuator. This adapter here is taking the place of the attenuator when we're actually doing the test. This connector will be connected to one end, and this will be connected to the other end. And so that ends up connecting to the unit under test, and this adapter right here is taking the place of the unit under test, and then the measurement side going back to the miniVNA Tiny. So now we're ready to do the calibration of the miniVNA Tiny in preparation of measuring the gain of our little amplifier. We are now ready to calibrate in preparation for measuring the actual gain of the little preamplifier. So we're going to go through the same steps as before. Calibrate, create. We're going to choose mode 1. Now my cables are out on the table, separated from one another. We're just going to read open. They're not connected to one another. And we sit back and take a break. It's now done reading the open. Now we'll connect our cables together through our menagerie of adapters, and we read the loop. It is done reading the loop, and as before, we could save the data for future reference, but we're just going to update. All right, now let's get everything inserted in our measurement loop here. The attenuator has to take the place of that BNC to BNC adapter, and the unit under test has to take the place of that UHF to UHF adapter. So this is what the final test setup looks like, with all of the adapters replaced by their appropriate pieces and parts. We have the BNC adapter being replaced by the attenuator. We have the UHF to UHF adapter replaced by the unit under test. And so now we can see what the results look like. Again, we have to set our frequency limits. 144 M for megahertz, 148 M for megahertz. We are ready to make our measurement. So we're going to do a single scan. We're not interested in the phase, so we'll shut that off. So we now export this data to the Excel file. And now let's process that data in the Excel file. So I've opened the two Excel files in my Excel. This one here is the attenuator file. This is the numbers associated with the characteristics of the attenuator. This one is the numbers associated with our measurement of the amplifier. So the first step in this process is to get them both into the same spreadsheet. So I'm just going to change the name of this tab to attenuator so I know which is which, and I'm going to move that over to the other guy here, which is 12, and I'm not going to click on that. So now there I got the attenuator, and I'm going to call this sys because it's the full system including the attenuator. And then I'm just going to create one more sheet here. So what I'm going to do here is I'm going to set this equals to this sheet here, this divided by 1 million. That way I end up with megahertz here. And then this one, sys is the entire gain, including this attenuator and everything, and we want to subtract out the attenuator. And that's just the attenuator, and it has all the same frequencies that this one has. And so we're going to say equals this one right here. See, it says transmission. We're going to take that value right there, and we are going to subtract this value right here, and that gives us the gain at that frequency. Now, what we're going to do is we're going to copy these. How far down does this go? 1071. A 1071. And we're going to go like this and all the way up to the top. And we're going to do paste. So we have frequency and we have the actual gain. So if we want to see a pretty picture of what that looks like, we just select both of those, do an insert, and we choose a graph. I like the smooth guys. And that gives us the gain over the frequencies of the 2 meter band. And we're going to just change this to a minimum of 15, give us a little more visibility to it, and move it to its own page. And it looks like we can go even 19 on that, huh? So let's do 19. There we go. So that's what the gain looks like. According to the miniVNA Tiny, it says that we have a gain as high as, well, 23.25 dB and as low as around 19.5 dB, depending upon where you are in the band. So let's just go ahead and do the same set of measurements using the Tektronix VNA. As before, the Tektronix VNA uses N type connectors. So I'm going to use the same N connectors, N connector on both ends. And then I'm going to use the SO239, the UHF to N adapters on those cables. Because the VNA is capable of having its source power adjusted down to minus 35 dB, I'm not going to need to use an attenuator. And that eliminates an awful lot of funky adapters. So let's go through the process of calibration and measurement to see what the gain is according to the Tektronix VNA. We're all ready to go to do our calibration and measurement of the gain of the RF preamplifier. First thing we want to do is set our start and stop frequencies. So 144 M for meg, and stop, it's already set to 148. Now remember, we need to also change the stimulus power. So we're going to go to Sweep Setup and Power menu, and here power level is right here. So we're going to change our power level to minus 35 dBm. So now our stimulus level is set where we want it. No need to use an attenuator. And so we're going to do a calibrate, and we're just going to do a simple response through. And S21, our source is port 1, and our measurements could be made on port 2. I need to connect my 2 cables together. Now that the cables are connected together, I'll click on through. Now it wants to do the isolation, which means I disconnect the 2. The 2 cables are laid out separately from one another so that as to enhance the isolation between them, and I click on isolation and I click on apply. All right, now we're ready to connect up to the unit under test and see what its gain is. The unit under test is now connected. We don't see anything on the screen because our scale is way off screen. So let's do an auto scale, bring it in. It's kind of googie, so let's average it to make it look nice and smooth. Now let's take a look at this data here. We have, at the low end, 17.45 dB of gain. our maximum gain is somewhere up in here at only 18.3 dB. Now it kind of makes you wonder. The miniVNA Tiny was telling us we had 23.2 dB of gain. And here, we're with the higher end VNA, it's 18.3. That's like 5 dB difference. Well, what's up with that? Well, it has to do with the accuracy of the measurements made with the miniVNA Tiny. I did a test thinking, oh, well, maybe it was the measurement methodology. So I went through the process, very similar to the same process I went through with the miniVNA Tiny. I even used the attenuator and everything, so that everything was about as identical as they could be. I went through this process several times. And funny thing, here is we have here the miniVNA Tiny, which I did 2 different ways, was very consistent, coming out to about 23 and a quarter dB here and 19 point something dB down here, pretty consistent. And then down here, I measured it with my Tektronix VNA, 2 different methodologies, one with the attenuator, one without the attenuator. Very much so again, the 2 blue traces are the Tektronix VNA. Funny, same kind of numbers we're getting here. And then we have here, I did the same measurement with the many times ancient Hewlett-Packard VNA, and again, very similar numbers. So the miniVNA Tiny very definitely is significantly far afield from the higher end VNAs in its measurement of the gain, even when I use exactly the same methodology and virtually the same hardware. So there you have it, how to perform basic 2-port calibration and measurement on a passive device like the Wacom Bandpass Cavity, and an active device like this RF Pre-Amp. If you have found this video helpful, please click on the like and subscribe to this channel so that you will be notified of future videos when they come out. In my next video, I'm going to go over some of the basic differences between the high-end VNAs and their more affordable cousins. And that will be the last video in this series. In the meanwhile, thank you so much for watching. Toodaloots.